This video is going to cover the section of 1.7 from AQA A-Level Chemistry, Oxidation, Reduction and Redox equations that look specifically at A-Level half equations. The video is going to cover a recap of simple half equations, and if you've not already looked over the half equations that you'd cover at GCSE, I suggest you look at my video Oxidation and Reduction first. Moves on to half equations involving multiple elements, combining half equations in acidic conditions, and looking at an exam question. Now, Year 2 chemistry also looks at half equations in alkaline conditions, but this video only covers acidic conditions. So, really quick recap of simple half equations. There's two half equations using GCSE level knowledge. Pause the video and see if you can complete those half equations. So first step for any half equation is to make sure that we've balanced the element. So if we look at the first one with lead, we've got one Pb on the left hand side and one Pb on the right hand side, Pb2 plus forming Pb4 plus. So we don't have to worry about balancing the elements, they're already balanced. The next thing to do is to look at the charges, and we've got a 2 plus going to a 4 plus. Now for something to increase in charge, it has to lose negative electrons. So we would need to have 2 electrons on the right hand side. Now we can check that mathematically, just making sure our charges are balanced correctly. If we think about the arrow being an equal sign, we've got a plus 2 on the left hand side, a plus 4 for the Pb4 plus, and then a minus 2 for the 2 negative electrons. Mathematically, plus 2 equals plus 2, because plus 4 minus 2 equals plus 2. That tells us the electrons are correct in terms of number and position in terms of left or right. For the equation on the bottom, we've got mercury, Hg2 plus, forming Hg2 2 plus. This one's a little bit strange to look at, but the first thing we've got to realise is that we have 2 Hg's joined together on the right hand side, and that means that we need 2 on the left, so we balance with a big number to get the stoichiometric ratio correct. Next thing, we think about the charges. Let's work out where the electrons go. We have 2 lots of this plus 2 here, so we actually have a plus 4 charge on the left, and on the right side we have a plus 2. Although it's Hg2, what we've actually got is Hg, Hg joined together like that, and then the 2 plus is across the whole of that, so it's only a plus 2. So plus 4 on the left goes to plus 2 on the right hand side. That shows us that the electrons have to go on the left, because we then have minus 2 plus 4. Mathematically that is correct, and that is our half equation. Now, if you are unsure about those simple half equations, as I said, best to go back and have a look at the previous video, Oxidation and Reduction, just to make sure that you do know where the electrons go and how to balance those half equations before we move on. But if you are ready to move on, I'd like you to just have a pause and think about how you might go about balancing this half equation. Now this one's an interesting one, okay, if we put it in a bit of real life context, this is nitrogen gas forming nitrates. This is the process that goes on in certain plants that are able to fix nitrogen from the air and turn it into nitrates to go into the soil, things like clover. The first thing to realise is that we've got oxygen present, we don't just have one element. And that's very common. Oxygen is present in lots of different compounds and lots of different molecules, so we find this quite commonly. Another compound that we find in many places is water, and that's something very important to remember. Now, when it comes to balancing half equations, there are a set of fairly simple steps that you can use to balance any half equation in acidic conditions. And as long as you remember those steps, you can balance any half equation you're given at AS level. Now, the first step for any half equation balancing is to balance the central element. Now, the central element is the element that is common on both sides, and that would be found in the middle of the molecule or ion normally if we were looking at the structure. So for this one, it's nitrogen. And we can see that we have 2 nitrogens on the left because it's N2, but only 1 on the right hand side. So the first thing is, as normal, is to add a big number to balance that central element. And that now gives us 2 N's on both sides. The next step is that we use water to balance any oxygens that are present. Now, water is present everywhere. It's all around us. It's in every living thing. So it's quite normal and quite sensible that we would use water, or we'd find water in chemical equations. So oxygens are on the right-hand side, and we have 3 in each nitrate, but we have 2 nitrates. So we have 6 oxygens that we have to balance, which means that we need 6 H2Os on the left-hand side, on the opposite side to where the oxygens are. And that balances our oxygens, 6 oxygens on the left and 6 on the right. But what we've done now is we've introduced hydrogens. So the next step, because we're doing this in acidic conditions, is that we add H+ ions to balance the hydrogens present in the water. Well, in the water we have 6 lots of 2 hydrogens, so we've added to this equation 12 hydrogens, which means that we need 12 H+ on the right hand side opposite the waters to balance the hydrogens. At this point we've balanced the nitrogens, the oxygens and the hydrogens that we've added, so elementally we're balanced. And so the final step is to count up the charges on each side and add electrons to balance the charges. So looking at this in terms of maths, we've got water which is neutral, and we've got nitrogen which is neutral. Put a little equal sign there. We have 2 nitrates which are negatively charged, 1 minus each. So we have a -2 that comes from the 2 nitrates. And then we have +12 for the 12 H+. So at the minute we have 0 on the left equals +10 on the right hand side. -2 + 12 is +10. Now with half equations we can only add electrons, and we've got to put the E- on either the left or the right. Now, if we were to put electrons on the left-hand side, that would decrease this charge. The left-hand side would go down. But what we need to balance these out, and we can only use electrons, so we can't put any electrons on the left. Instead, what we've got to do is we've got to add electrons on the right-hand side to decrease this positive charge here. So we need to put 10 electrons on the right-hand side, and that then balances out our charges on the left and right and makes them equal. They don't have to be 0, they just have to be equal on both sides. So just to recap those rules, which are the same for any acidic half equation that you might come across. Step 1, balance the central element. Step 2, add waters to balance the oxygens on the opposite side to where the oxygens are originally. Step 3, add H+ to balance the hydrogens present in the water. So the H+ go on the opposite side to the water you add. Step 4, count up your charges on each side. And the final step, add electrons to balance those charges. I'm going to do one more example, which is slightly more confusing to look at. This is dichromate forming chromium 3+. Very common for organic chemistry. You'll be learning a lot about that if you haven't already. Also is present in the demonstration if you've ever seen the dichromate volcano, which is quite exciting. Look that up if you've not seen the video. So, first of all, balance the central element. Now our central element in this one is chromium. We have 2 chromiums on the left-hand side. We need to make sure that we have 2 chromiums on the right. That's step 1 done. Step 2, add waters to balance the oxygens. Well, we can see we have 7 oxygens on the left-hand side. We need 7 on the right, so we add 7 H2Os to give us those 7 oxygens on both sides. Step 3, add H+ to balance H's in the water. So we've added 7 H2O on the right, that's 14 hydrogens. We therefore need to put 14 H+ on the left to balance those out. Step 3 done. Step 4, count the charges on each side. So we have plus 14 from the H+, plus a -2, put these in brackets. We then have 2 lots of +3 from the chromium 3+, and 0 from the water. And so we have a +12 on the left-hand side, and a +6 on the right. And remember, we can only add electrons. We've either got to put the electrons on the left or the right. If we put the electrons on the right hand side, then that is going to make that +6 get lower. We need the two sides to even out, so we want to put the electrons on the left hand side to lower the value of the +12 until it is equal to +6. Now that means that we need 6 electrons on the left hand side, and we can check that by putting that on the left, because -6 + 12 comes out to be +6. And that is the half equation for dichromate forming chromium 3. That's a half equation that you do need to know throughout the course, so it's a good idea to make sure you're familiar with it. So, your turn again. Pause the video and attempt the following half equations in acidic conditions. Make sure you follow the steps, count your elements at each point, and make sure you do check your maths for each one. So, question 1, we've got sulfate forming sulfur. So I'm going to just write this out again to make it a little bit neater. Spread it out a bit. So first of all, we're going to balance the central element. Well, we have 1 sulfur on the left and 1 on the right, so that's already balanced and we don't have to worry about step 1. We move on to step 2. Balance the oxygens by adding waters. 4 oxygens, we need 4 waters. We've added hydrogen, so we need to make sure we've got H pluses to balance those. 4 H2O means we need 8 H plus on the left hand side. And then balancing the charges, everything on the right is neutral, S0 and H2O is 0. And on the right hand on the left hand side, we have a -2 and a +8. So that is a +6. And that means that we need 6 electrons on the left to complete that half equation. For question 2, it's iodate forming iodine. So first step again, balance the central atom. This is iodine this time. We have 1 iodine on the left, but 2 on the right. So that means we need 2 iodates. Next step is to balance the oxygens using water. Well, we've got 6 oxygens on the left-hand side, 2 lots of 3. So therefore we need 6 waters on the right-hand side. Next step is that we need to balance the hydrogens that we've added because of the water, and we need to balance that on the opposite side with H pluses, so 12 H plus. And finally we need to balance the charges by adding electrons. So we have here a +12, -2, again it's 0 on the right hand side, so +10 equals 0. That tells us that we need to fix it mathematically like that, and therefore it is 10 electrons on the left hand side. Question 3, VO2 plus forming VO2 plus, another common half equation from year 2. You could be asked to do these the opposite way around. First of all, balancing the central element, we have 1 V on both sides, so that's not necessary. Next step is to balance the oxygens. Well, here we have oxygens on both sides. We still need to add water because we've got 2 oxygens on the right and only 1 on the left. So that means we need 1 water on the left-hand side. That will give us 2 O's on the left to balance the 2 O's on the right. We then need 2 H pluses on the right-hand side. And then the final thing to do is to look at the charges. So on the left-hand side we have 0 plus 2, and on the right-hand side we have +1 plus 2. So +2 equals +3. The electron has to go on the right-hand side to balance those charges out. Final one, number 4, SO4 2- forming H2S. Balancing the central element first. Central element is S. There's 1 S on each side, so that's fine. The next step is to balance the oxygens. We have 4 on the left, so therefore we need 4 waters on the right hand side. Next step is to balance the H's, but this time we've got hydrogens present originally as well as the water that we've just added. So we have 8 H's from the water as well as 2 that were present originally in the hydrogen sulfide, so therefore we need 10 H pluses on the left hand side. Final thing, balance the charges. We have +10 minus 2 on the left and 0 on the right hand side, so that is +8 on the left overall. Be a -8, so it's 8 electrons on the left. So once you're clear on how to balance half equations in acidic conditions, we now need to look at combining half equations, just like we did with the simple half equations. And we're going to have a look at an exam style question, and it might look a bit daunting to begin with, but if you read the question, you'll notice that there's loads of information in it. Potassium manganate 7 can be used to determine the concentration of iron 2 ions in an acidified solution. In the titration, the potassium manganate 7 is the oxidising agent and it is reduced to Mn2 plus aqueous. The Fe2 plus is the reducing agent and is oxidised to Fe3 plus. What is the full redox reaction? Now this is actually a titration that you need to know about for Year 2 chemistry, but it can come up in Year 1 exams. And as I said, it looks very wordy, but there's loads of information in it that's really useful. So first of all, the first sentence is just giving a bit of background about what's going on. So it's telling you that it is used in an acidified solution and that we've got iron 2 and potassium manganate. It is really important to read the whole thing because that acidified solution is really important. The second sentence tells us that we have manganate 7, and that's an ion that it's necessary for you to know. And manganate 7 is the old permanganate ion, which is MnO4 minus. The question tells us that potassium manganate 7 is the oxidising agent and that it is reduced to Mn2 plus. Now, if the manganate is being reduced to form Mn2 plus, then that means that we've got a gain of electrons. And that should tell us that the electrons actually go on the left-hand side of this reaction because the manganate has to gain. So that's useful information. The last sentence, the Fe2 plus, is the reducing agent and is oxidised, so that's a loss, to Fe3 plus. So we have Fe2 plus turning into Fe3 plus, and it's telling us it's an oxidation. We've got a loss of electrons. That means the electrons have to go on the right hand side to show that the Fe2 plus has lost the electron. And because it's going from 2 plus to 3 plus, it's just going to be 1 electron. So that equation is quite nice and easy to balance. Now the full redox reaction is the question that they're actually asking for. And that involves us doing the two half equations, one of which we've done already, and combining them, cancelling electrons to form the full ionic redox reaction. So let's balance the manganate reaction. MnO4 minus forming Mn2 plus. Central element is Mn, and we've got 1 on each side, so that's balanced. Next step is to balance the oxygens. We have 4 on the left, so we need 4 waters on the right hand side. Now that we've done that, we've added hydrogens into our half equation. There's 8 hydrogens on the right, so we need to use H pluses because this is an acidified solution. So we're going to have 8 H pluses on the left hand side. And the final step is to look at the charges and to balance them out with any electrons. So we have plus 8, minus 1 on the left hand side, and we have plus 2, 0 on the right hand side. So that's a plus 7 on the left and a plus 2 on the right. That means we have to have 5 electrons on the left hand side. So these are the two half equations. Now the next thing to bear in mind before we combine these and cancel out any electrons is that the electrons have to be equal in the two half equations. It's the Fe2 plus that is providing the electrons to allow the manganate to turn into Mn2 plus. Now one Fe2 plus only provides 1 electron. We need 5. So that means that we need to start with 5 Fe2 plus, we will make 5 Fe3 plus, and that will produce the 5 electrons that we need. So what we've done is we've times that equation by 5. That then means that we can cancel out the 5E minus on the left and on the right for the two half equations, and we can just then put everything on the left hand side together, everything on the right hand side together, and that will give us our ionic equation. So it doesn't matter what order you put these in on when you write these down, as long as everything that's on the left is on the right is on the left hand side and everything on the right is on the right side. So 8H plus plus MnO4 minus plus 5 Fe2 plus forms Mn2 plus 4H2O and 5 Fe3 plus. And there's the full redox reaction. So second time for this video for you to have a go. So we've got a couple more exam style scenarios. So pause the video and complete and combine the following pairs of half equations to produce ionic equations, just like the previous example with the manganate and the Fe2+. So we have the first one being zinc forming zinc 2+, and the second example nitrate forming nitrogen dioxide. And then number 2, we have iodate forming iodine and iodide forming iodine. So answers to question 1. We have zinc forming zinc 2+. For that to happen, the zinc has to lose electrons to form the zinc ion. Therefore, 2 electrons have to go on the right hand side. And we can just double check the maths there. 0 on the left, and then we have +2 -2 on the right hand side, which is also 0. So that is balanced. The nitrate to nitrogen dioxide. We've got oxygens present, so we're going to have to use the extra steps that we've learnt in this video. So, balancing the essential elements, we have N present once on the left and once on the right, so that's already balanced. We need to balance our oxygens by adding waters. We have 3 oxygens on the left and 2 on the right, so we need another 1 on the right hand side, so just 1 water molecule. We've then added some hydrogens, so we need 2 H+ on the left to balance out the hydrogens. And then finally we're looking at the electrons. So we have +2, -1 and 0. So that is +1 = 0. Therefore we just need 1 electron on the left hand side. Now because we've got zinc producing 2 electrons and 1 nitrate only using 1, what we need to do is we need 2 lots of that bottom equation. So we're going to have 4 hydrogens, 2 nitrates and 2 electrons, forming 2 NO2 and 2 H2O. Overall, our equation is zinc plus 4H plus 2 NO3 cancel out the electrons, and that forms zinc 2 plus 2 NO2 plus 2 H2O. And the answer to number 2. Have already done the first equation earlier on in the video, which is a little bit of an error, but we'll carry on doing that one anyway. So iodate forming iodine. First of all, balancing the essential elements, we have 2 I's on the right hand side, but only 1 on the left, so we need 2 iodates. We then need to balance the oxygens by adding waters. Well, there are currently 6 oxygens on the left hand side, so we need 6 waters on the right. We've now introduced 12 hydrogens thanks to the 6 waters, so we need 12H+ on the left hand side to balance those out. And the final thing is to balance the charges. Well, currently we have a +10 on the left hand side, because 12 plus and 2 minuses is +10, and we have 0 on the right hand side, so we need 10 electrons on the left to balance those out. The second half equation on this slide, well, again balancing the central element first. I- on the left is 1 iodine, we have 2 on the right, so we need 2 iodides. We don't have any oxygens or anything here, so this one's a fairly simple one. We're now looking at what's happening to the charges. We have 2 negatives on the left that have disappeared on the right hand side, so what has to happen is that the electrons are lost by the iodide, to form the iodine. So we have 2 E- being produced on the right hand side. To look at this overall, we have 10 electrons being used by the iodate in the top equation, but we've only got 2 being produced in the bottom, so we therefore have to have 5 lots of the bottom half equation. That would then give us the 10 electrons that we need. So 5 times 2 would mean that we have 10 iodides, I keep making that error. We would have 5 iodines and we would have 10 electrons on the right. So we can therefore then cancel out all of the electrons from the left and right, and we can add these together. So 12H+ plus 2 iodate plus 10 I- forms 6I2, because we have 5 plus the 1 at the top, and 6H2O. Now in an exam you would be able to leave it like that because multiples are always marked correct if the ratio is correct. So 12, 2, 10, 6, 6 is absolutely fine, but we can put this down into the simplest ratio, so we can divide everything by 2, and that would also give us the correct answer. As well, but as I said, unless you are told to give it in the lowest ratio, then as long as the multiples are correct, it will always be awarded.